Let's see example 2 about polarization. It's very important. Okay, we have here a sphere shell as shown in this figure has epsilon equal to epsilon naught for region 0 to 1 to A. So the inner part here, which is a vacuum, and then we have epsilon equal to epsilon naught epsilon r for A less than B, R less than B. So this is between A and B. If a charge Q is placed at the center of the shell, find first polarization vector between A and B, because polarization vector exists inside dielectric material. And then we have to determine bound volume charge density at the same region, and last question, bound surface charge density at R equal to A and R equal to B. Okay, like I mentioned earlier, the bound surface charge density may exist on both surfaces of the dielectric. That is the situations. For the solutions, for point charge, the electric field intensity is E equal to Q divided by 4 pi epsilon R square. So because we have maybe the dielectric material, so we leave it as an epsilon. The unit is volt per meter. While the electric flux density equal to epsilon E. Therefore, we can write the D equal to Q divided by 4 pi R squared in the direction of R, coulomb per meter. Therefore, we can define D equal to Q divided by 4 pi R squared in the direction of R, coulomb per meter. So, for polarization vector in region between A and B, so we can use this formula, P equal to D minus epsilon naught E. So, D equal to Q divided by 4 pi R square minus epsilon naught Q divided by 4 pi epsilon R square. Okay, inside dielectric, epsilon equal to epsilon R epsilon naught. Therefore, we change epsilon equal to epsilon R epsilon naught. This one can be cancelled out. So, our polarization vector equal to Q divided by 4 pi R square in bracket 1 minus 1 over epsilon R in the direction of R, coulomb per meter square. B, bound volume charge density. Okay, between A and B. Okay, the rho VB is equal to negative divergence of P. So, this is the spherical coordinate. So, we have to refer to the table of divergence. So, we use the spherical coordinate. We have the R component, theta component, and phi component. However, when we determine the polarization vector, we can see that our polarization vector only have the R component. Okay, so we just use the R component here. So the rest will be 0. So the polarization equal to negative 1 over R square del R square divided by del R cube over 4 pi R square in bracket 1 minus 1 over epsilon R. When you solve this, it becomes 0. Why? Because here we have R square, we will cancel out R square with this R square. So our P do not have variable R anymore. Therefore, the solution equal to 0. Next, we go to the bound surface charge density on dielectric surface. To find the bound surface charge density, or rho SB, we have to dot product our polarization vector with a vector normal to the surface of interest. Well, let's see our structures. So we have the dielectric structures between A and B. Therefore, we have the rho SB at R equal to A and rho SB at R equal to B. Then we have to observe where the vector normal to that surface. Let's consider when R equal to A. So we have the vector normal to the surface going along negative R directions. At R equal to B, so the vector normal is going along R directions. Because this is our surface, so this is vector normal to that surface. Well, so at rho SB R equal to A is equal to polarization vector dot product with negative R. This is our polarization vector, and then you have to change our R equal to A. So that's why our P is equal to Q divided by 4 pi A square, 1 minus 1 over epsilon R in direction of R dot product with negative R. So you got SB R equal to negative Q divided by 4 pi A square in bracket 1 minus 1 over epsilon R coulomb per meter square. Using similar argument for rho SB R equal to B, the difference is we have to dot product our polarization vector with R because the surface facing R directions. And you have to change your R equal to B. So you got here P equal to Q divided by 4 pi B square in bracket 1 minus 1 over epsilon R direction of R dot product with R. And your final solution will be Q divided by 4 pi B square in bracket 1 minus 1 over epsilon R coulomb per meter.